All right, guys. We actually have a worksheet after this. That's homework. So, because we're still playing catch up, trying to get enough done so that you can actually pass your AP exam. Okay, so starting 19. So we're putting 18 and 19 together. We are now going to talk about circuits. So we are talking now about some kind of a pathway. So we're going to put all this knowledge together. We just had Ohm's law, V equals IR, and saw the relationship between voltage, current, and resistance. I'm going to do it again a little bit. We're going to do an analogy of a mountain stream. Okay, so here is a tall mountain. Actually, think more like waterfall kind of thing. And so what about the height of the mountain? We want to make an analogy to voltage, current, and resistance. The higher the mountain, right, the bigger the difference in elevation. What would that correspond to for voltage? So that would be the voltage. Why? Because in a sense, it gives you more potential energy. Remember, voltage is potential energy per charge, and it's a difference. What matters, right, with the mountain is not the total, it's really the top to the bottom, right, if you're going to figure out how fast a stream will run. And the flow of the water would be, that's our current, okay? So we could get more flow going down. That's our current. And then all our boulders in the way would be slowing down the current, and so that would be our resistance. Okay, so there's our little analogy, and now we're going to start to worry about now circuits and how we can make the stream, how we can do these streams, and how we can arrange them. And one way is to have just think of a lazy river kind of thing, where it's one pathway only, and we call that series. And a series circuit, so anything you have in there, the resistors and everything, the light bulbs, whatever you have, are all connected in a row, end to end, one after another. You saw that on a worksheet where I asked you to draw two batteries or cells in series, and you drew them end to end, a plus to a minus situation, okay? There is only one pathway. It's one road, okay? Imagine having only one way to get to school. All right, the resistances add up. Every single resistor, all right, is increasing the resistance. It's like having a road and having a bunch of potholes, and every pothole overall is going to reduce the flow of cars on the road, okay? Okay? Or how about a speed bump, right? A bunch of speed bumps. Okay, so our total is R1 plus R2 plus all of them. So in this case, can we do this? What is my R total? Sometimes called R equivalent. The equivalent resistance, if I wanted to replace both these resistors with just one resistor, one equivalent, it would be 2,000 ohms, right? So you can either say R total or R equivalent. I use them interchangeably. This is not hard. My R total here? Okay. I don't have to say anything more about that. Series circuits are really easy in terms of finding the total resistance, because you just add them up. Okay? All right, electrons move from where? The negative terminal of the battery. Okay, now, at the same what? Current. Yes, so current, which is a rate to the positive. Okay, so unlike the speed bump, do you know what you do with speed bumps if you're in a car? You go really fast to get to the speed bump, and then you go bump, and then you go really fast, and you slow down, and then you go bump, right? Can't do that. Electrons can't do that. You know why? Electrons are not spaced out from each other. This is a traffic jam. This is bumper to, this is like when you get out of school. Bumper to bumper. And if at one point someone is going slow and you're bumper to bumper, can you go fast? No, because you're waiting. You're the car waiting for the car in front of you to move. And you can all kind of move at the same time. That's what electrons are like. It isn't like you go, whoot, 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 you know, and wherever. If you're in series, current is the same everywhere. Not fast and slow and fast and slow. Whatever I is the same everywhere. And in fact, the I total, if you know the current, we often say, if you know the current leaving the battery, that's everywhere. The current leaving the battery, the cars pulling out from Dexter High, and if there's only one way to go, is the same as the current then everywhere. And the current entering the battery to the other side, right? Negative, positive. So this is official, right? This is electron flow, all right? It's I. It's all the same I, okay? So a traffic jam does not just affect that spot, all right? All flow is reduced. And here is a formula. So how do you find the current? Well, you take the voltage and you divide it by the equivalent resistance, okay? Or we can say, right, what did I write? Just I total is V total divided by R total, okay? The more resistors or devices, the blank the current.
Less.
Right. The lower the current, if we want to make it sound a little nicer. Okay? All right. Do you want to do some calculations on this then? So, I didn't label this. Let's make this 12 volts. Okay? Like a car battery. Okay? And here I have 1,000 and 1,000. So we already said the R total here is 2,000 ohms. And I want to find the current, so I'm going to do V over R, V total, 2,000, okay, over, right? What? Oh, what's my problem? And it wasn't making any sense. I'm so sorry. I'm so sorry. I know it's Monday. Okay. All right. And when we do that, what are we going to get? Something small. 12 divided by 2 is 6, but we know we have some decimals, so it's 0.006.
Yeah.
What unit? Amps. Okay, yeah. And what else? How else could you see that written?
6 times 10 to the negative third. Am I correct? 6.
Milliamp is what often you'd see, or your multimeter would give it to you. All right. I'm being really sloppy with my significant digits. We're going to remember these are always within 5%, so that means I have at least 3 sig figs here. I'm just trying to make this nice just to go through this right now. Okay? All right, so we have 6 milliamps. Where is 6 milliamps? Everywhere. So 0.006 amps here, 0.006 amps here. Yeah? All right. So that's cool. How about this case? Let's do this one just in case. I'll make this one 6 volts. All right. We already said our total was 4,000 ohms. And so can I do it right this time? V over R, V6 over 4,000. All right. And what do I get? 0015. All right. I had half the voltage and twice the resistance. So does it make sense? I have a fourth the current?
Yes.
Okay. So I'm going to label, I like to do this, and you go, it's a bit redundant, Miss Jones, because I know it's the same everywhere. I know. But if you connect information like this, I know 2 things here. I know 2 things. Whenever you know 2 things and you have a great formula like V equals IR, we can find the third. And what's missing? What don't we know? No, we know charge is Q. And Q, we know Q per second. That's called amps. But we could do power. That's a good one too. How about voltage? Do we have voltage? No. I know the voltage of everything. But if you read the next line, it says voltage gets divided among the devices. Now, when I say divided, It's not always like motherly, everyone gets the same amount. All right? It's proportional to their resistance. Let's do this one first. Okay? It's proportional to the resistance. Guess what? The total voltage is I times R times. Notice the I is the same for everyone, so I can just call it I. Times R1 plus I times R2, whatever. This is the total. It gets divided. So what is this going to be? V equals IR. Here's my I, 0.006 times 1,000. Can we do that without a calculator? 6 volts. Okay? So I'm claiming this now is 6 volts. Okay? Guess what this one's going to be? Okay. Now, why? 2 reasons. One is it's proportional. Since this is 1,000 and this is 1,000, they should both get the same. Or did you realize that the V total is V1 plus V2, etc.? And I just have 2, and this one's 6. 6 plus what equals 12? It's going to be 6. And I don't care which way you use to solve for that. Either you can go 6, I know that, or if this was 8, then you would know this is 4, and you wouldn't have to do the division if you don't want to. Okay? Is everyone good on this? People go, what do you mean the voltage? Yeah, the voltage. How about we understood that with batteries, that the voltages were additive. Same thing here. This gets some of the voltage. Can I show it like a stream again? If I start up here and I have one resistor and I have another resistor, and I call this the voltage, do they all get that drop? No. Do you see they only get part of the elevation? This gets this part of the voltage. If this whole thing was 12, and this gets part of the drop. Okay? So it's like a stream and a stream with one total elevation change. I don't know if that helps you, but that helps me. Okay? All right. How about the other one? Did someone without a calculator with smarts solve this one for V?
Yes.
I want to know V.
I did.
All right. And
It should go 1.5, 1.53.
okay. Because I think he used the proportional thing. He knew it had to add up to 6, all right? And that this was 2,000. This had to be twice as much as this, all right? So this gets 3, and these get to split. They all add up to 6, and yet this is twice as much as these. If you don't want to do it that way, you could take this times this is this. This times this is this. This times this is this. Do you see there's lots of checks and balances with this game that we're going to be playing? It's very Sudoku-esque, these questions I'm going to be asking. You need to find out something to find out something else, but then you can check to see if you did it right. Okay. All right. This is all good until I turn the page. Okay, do you know everything I just taught is gone? Everything we just did is the opposite. Everything that we solved for first, we solved for last. Everything that is the same is now different, and everything that was different is now the same. I compare this one in chemistry. I teach ionic and covalent bonds, and it doesn't matter which one I start with. Whatever one I start with, everyone's good with, and then when I add the second one, people mix the rules, and then you know nothing. Nothing works. When you switch rules, when you mix up the rules, things don't work anymore. So make sure you create this divide in your mind of what's happening. This is parallel, okay? Now, some people look at this first picture as drawn, they go, that's not very much parallel, Miss Jones, because this is intersecting with this one. Thank you. Okay. Devices are on separate paths. I'm telling you, the road splits, and you have a choice of 2 or more roads to pull out of Dexter High, okay? These roads still have a speed bump, but you don't need to take both speed bumps, okay? Some roads have more speed bumps than others sometimes. So there are some pathways that are more advantageous. Okay? All right. Current from the battery does not have to go through all the devices, nor do they have to go equally. If this was Dexter High, and you are this is the parking lot drive, and then you have a choice between a road and a road and a road, and this road has half the resistance of the other two roads, where are most cars going to go?
Where do I live?
This is like, right? The fast road. Where do I live? Look, you all have to come back to, you live here. Okay. Okay, can I go underground? Okay. Can we fly? No. Okay. Some people have a dead battery. I know that. Okay. But so here, now they split. Now, do you see how I wrote this one like this? When this current, it looks like it splits at one point, and the paths are the same length. The length, do you realize this is split at the same time 3 ways? And you go, no, Miss Jones, it's split, and then it's split again. Do you realize this segment of wire is going to be insignificant? It is the same as if I put this junction right there and split it 3 ways. Why do people write it like this? Because it's easier, and it's pretty and square. Okay? That's why. And they look parallel to make people happy. But don't think this way was the longer drive, because it's just a wire, and the wire is close to being insignificant. It's very insignificant compared to the resistors. Okay, so now this is a 2-way split. This is a 3-way split. Okay, all right. And current, does everyone see the current would be the greatest here? Okay, all right. All right, so facts. I's are not the same unless the R's are the same. The first example, R's are the same. As much current goes this way as this way. It was like a toss which way to drive, right? They were equal in difficulty to drive. So half would go this way, half. So if you knew the total current, right, this would get half of the current, this would get the other half. Does that make sense? Logical? Okay. All right. Does everyone agree that if you know the total current leaving the battery, everyone listen, total current leaving the battery, that all the individual pathways better add up to the total? Yes? Because that would be a problem if you send out, or you have a certain rate going in, let's say 0.5 amps going into an intersection, they split, and when they come back together, it adds up to 0.2. Like, you'd go, something's wrong there, okay? Or the individual paths don't add up. Okay, so total current leaving the battery adds up to all the pathways. Okay, how about this? Remember I said everything's opposite? Because, remember how voltage was different with series? Guess what? Voltage is the same. Because the battery is directly across each device, connected to each end of every resistor, the voltage is the same everywhere. Let's look at this picture again. Do you see that these wires, the plus, so plus 12, 0 volt, do you see they're connected to both? Okay. You know what, if I want to do the stream thing, this is a bifurcated stream. Ooh. All right. So this is 12 volts, and you have 2 parallel streams running. So they both get the 12. It's not one stream, stop, and another stream. Okay? All right. So, I can label this. Now that I just got this is 12. How many volts is this?
12.
How many volts is this? Can I take 12 and 12 and add them to get the total? No, because that's a rule for series. Okay? Ooh, you have to be careful when I have my phone and I talk to this chapter. My phone starts talking because I say series, and she gets excited. All right, she tries to answer the questions. All right. How about this? These don't have the same resistance. So tell me about the voltage. It doesn't matter. They're all directly connected.
666.
I know.
Whoa.
Miss Jones is the devil again. Okay. All right. So, I total is V over R1 plus V over R2, dot, dot, dot. Current is blank then if in series. Current is blank. What do you think? Current is more or less?
More.
If you had 3 pathways to get out of the school, even though every pathway had a speed bump, are you going to get more? What is the rate of cars leaving the school if there was 3 dirt roads instead of 1 dirt road? There's 3 roads to get out of the school, and one, let's say one was getting over the grass. Wouldn't some people take that? Can't you still get more people? No matter what, it's more. Way more.
North?
You are so mean.
You almost killed me once.
All right.
And it works.
I'm gonna share after this video people's spelling and it's you, Adam, what happened, because it got bad today.
Oh, did it?
Oh, it got bad. Okay, I can't even say it on camera. Okay, all right. The misspelling led to disaster. Okay, all right. Okay. Ooh, guys, you're gonna hate this.
Great.
How to find the equivalent or total resistance, really where you have to start paying attention because you're going to screw it up, is 1 over the R total turns out to be equal to 1 over R1 plus 1 over R2 plus dot, dot, dot. You love fractions. I know it, and you're so good at them. Not. Okay, so let's do this one. All right. 1 over the R totals, 1 over 100. Oh, can I do the one above? Let me first do this one. Hold on. Let's do the easy one first. Can I do this one? Can you tell me what 1 over 1,000 plus 1 over 1,000 equals 1 over R total? What's my R total going to equal?
5.
Do you know I still have people that don't know you don't add the denominators when you add fractions? Okay. So let me first do this. 2 over 1,000, and what's that going to be? Don't I take the reciprocal?
500.
Right, it's 1,000 over 2, which is 500. What's significant about that?
It's half.
It's half. You got 2 the same. Don't do the math. We now know it's half. I can replace this with a 500 ohm resistor. There you go. Okay? All right. Can you do this one? Can you do it in your head?
250.
Because you can't do fractions in your head? But can you be smart? No, you can't do that. Okay.
It's
I can do 1 over 500 plus 1 over 1,000 plus 1 over 1,000. And then I have to find common denominators. Oh, and that would be 2 over 1,000. And then it's 4 over 1,000. It was 1 over, and then R is 250. Now, could you do it fast? Didn't I just teach you something? Didn't I teach you that 1,000 and 1,000 is? 500. And didn't we say if you have 2 of the same in parallel, it's half? But bam, 250.
Skadoosh.
Isn't that nice? That's if I give you nice numbers. If I give you 172 and 18, you're going to be mad, right? Okay. This is AP. Okay. All right, let's go back. Can you predict what this one's going to be now?
Third of 100.
All right. You can. Look, you don't have to find common denominators. Do you realize you could turn everything into a decimal? Isn't that amazing? I should have to teach you how to do math, but, right, it's 1 over 100, right? It's 100 over 3, so it's 33.3 ohms. Okay? All right, and I just did that one. Oopsie, right? Okay. Oh, wait, I need to find out everything about this before I do that scary thing. I just found out the equivalent is 33, all right, and I know this is 12 volts. I want to find out everything about this. Can I already label this 12 volts, 12 volts, and 12 volts? Can I already find the total current leaving the battery? If I know the total voltage and the total resistance, can't I find I total?
Yes.
Okay, and so I is V over R, so that is a total of 12 and a total of 33, all right? And so what do I get? Help me, people. Is this one I did?
Yeah, 20, 36, 36, 36, 36.
Okay. All right, I'm going to believe you. Okay. How else can I do this? Can't I do individual ones? Can I find the current through the first one is the voltage of the first one divided by the resistance of the first one? So what would I have? 12 over 100, what's that?
0.25, 0.12.
0.12. How about this one?
0.12.
This one. And what do they add up to? Okay. Isn't that good news? When they all come together, they will equal. All right. How about this one? 6 volts, 6 volts, 6 volts. I could find I total if I want. I do 6 over, didn't we say the equivalent was 250? Can I find that work here on my paper? 6 over 250 is 0.024. That's my total. I'm going to label it here, 0.024 amps. So I know, 0.024 amps. I know when they all come together, they better add up to that number. So what is the parts? How do I do each one? So I can find individual current. Do you notice I'm doing current of each place last when before I did voltage last for series? Okay? All right, so I equals V 6 over 500. This one is 6 over 1,000. This one's 6 over 1,000. So what's this one going to be? This is I'm going to do the easiest one first. I can do this one in my head. 0.006. And if this has half the resistance, what's the current? Twice as much, 0.012. What do these add up to? I hope the total. I don't mind you being wrong, but I don't like it when they make no sense. Okay? All right. Last thing. Now that you know series and parallel, it's kind of like when you learn math and you learn about addition and subtraction and multiplication and division, and then you get a problem where you have all of it in there, and you've got to know what you have to do first. That's kind of this. All right. Here, is this series? Is this parallel? It's both. What rules can we apply right now? None. Okay. So we better fix this. So first of all, it would help if I actually had numbers on this. So let's set the problem here. All right. I made this 6 ohms, just really small numbers, just for easy work. Okay. Here's what we have to do. Just like in math class, we have to simplify the circuit. Can you see something we could get rid of? Can I add this and this together? No, because this is in series with but so is this. So, yes.
Well, I was just going to ask the question of what we can simplify.
Okay, what can we simplify?
The 6 ohms and the 12.
The 6 and 12. These are in pair. Can't we eliminate that? Turn it into one thing. So I'm going to redraw my picture. And please, please, please redraw pictures. It's kind of like when your math teacher asks you to do steps, like simplifying an equation, and they want to see those in-between steps. It's helpful. I'm just pleading. It's going to help you do problems right as things get complicated. So I have to figure out this is still the same. I got to go 1 over 6 plus 1 over 12 equals 1 over R total. I can make this the same. So this would be 2 over 12. Does everyone see it's 3 over 12 is 1 over R? And then then I do 12 over 3, which is, can I tell you something? Have you figured out the equivalent resistance of anything in parallel is always less than either one? If it isn't, you did bad math. Okay? If you got 7, you would know that's wrong. Okay? It has to be less than either one of those. And this is 4. So we're going to, we hope it's right. Okay. Now what? Now we're home free, right? We can simplify this just into 1. And I can add that. I have 10 ohms. Oh, I never told you the voltage. Let me look what I decided. We made it 12 volts again. So 12 volts. Everywhere was 12 volts in this picture. But everything didn't get 12. The individual resistors didn't get 12 volts. So the only thing we know 2 of our 3 things for Ohm's law for is this picture. So when you work a mixed circuit, you simplify it all the way down, find out everything you can here, apply it to this picture, find out everything you can do here, and apply it to the picture I want to know everything about. Okay? So let's go over here, and what do we need? What's left? Current. I total. That's going to be the current leaving the battery in the future, right? So I total, V over R, I got 12 over 10, right? So, right, we got 1.2 amps. Yeah? So where is 1.2 amps? Everywhere, right? Now, let's go back here. What can you tell me about the 1.2? Where does it exist?
Everywhere.
There's only one path. If there's only one path, the current has to be the same everywhere. So I'm going to go like that. Or if you'd like, 1.2 amps, 1.2 amps coming into the battery, 1.2 amps, leaving the battery, 1.2 amps everywhere. But you know what's awesome about this? Do you notice I just labeled, this is this. Do you see I labeled it with 2 things? That means I'm home free, right? What can I find out? What's left to find out here? Because we're series, do you remember voltage was last for series? So voltage equals I times R. So I do I, 1.2, times 6. All right, and what do we get? All right, 7.2? If I'm not crazy? So I'm going to label this 7.2 volts. Then, I blobbed that up, 7.2. So, could that be right? The total voltage is 12. Could that be right? If this was 17, you would go, oh crap, what did I do wrong, right? Please don't have things that these things are more than the total battery. Yeah? Okay. It could be, right? 7.2. Okay. What about this one? And isn't it more than, shouldn't it be more than half? Because this is proportionally more than that? Okay. All right. Let's do this one. So what are we going to do here? V equals I, still 1.2, times 4. Right? What do we get? Whoops. 4.8 volts. And what's the big check? Whew. Okay. Do I know everything? Almost. I know everything here. I know this is 7.2 volts, and I know the current, right, was 1.2 amps. Okay. What do I know here? Please be careful here. Right now, everyone needs to stop and make sure they do something right. Do I know the currents here? Can I take 1.2? All I know is it adds up to 1.2. So screw the current. This is parallel. We can't do current until, what about the voltage? This is the question. Do I label each 4.8?
Yes.
Or do I label them each half of it 2.4 and 2.4? This is the question. And we're going to think about this. The voltage, remember like the stream? The stream was 7, but does elevate, this? Here's the stream. You had a double waterfall that went into a single waterfall. We know here to here is 12. We know this is 7.2. Do I label these 4.8 and 4.8, or do I label it 2.4 and 2.4 if this is the elevation of 12? We can label, doesn't this one drop 4.8? Isn't this one also allowed to drop 4.8? You don't have to add these total to find out the total elevation of 12. Does everyone kind of get that? Because they're running next to each other. Okay? All right? So, 4.8. How about if I tell you here to here is 4.8 and they both get to count it? Okay? Because here was 4.8 voltage drop. Okay. Now we're home free, aren't we? Because anytime you have two things, you got a third. So the last thing you solve for in a mixed circuit is the current in the parallel section. So I equals V over R. Now, I use this V, not that V, right? And I use this resistance, not that resistance. Okay, whatever's in this picture here. So I have 4.8 over 6. And this one I have, what do I have? 4.8 over 12. Because this one's going to get half the current of this one. And what do I get? I don't know. I don't remember. 4.8 over 6 is 0.8. All right. And then 4.8 over 12 is 0.4 amps. Okay. How do we know if that's right? How do we know we didn't go wayward? 0.4, and because it adds to 1.2, the total current. The current was 1.2 here. It split. Doesn't it make sense? In fact, you could have done this in your head just with proportions, couldn't you? This is 1.2. We know this should get twice as much as this one. And we know it has to add to 1.2. And the only answer for that is 0.4 and 0.8. And we know everything now. We know 3 things about every location, and we are done. Ta-da! All right. Happy? All right. Make sure you keep those rules separate. What's true for series, what's true for parallel, don't mix the two. That's pretty